What if a star's magnetic field could outshine the entire universe in a single burst? On December 27, 2004, a magnetar 50,000 light-years away unleashed a flare so powerful it bent Earth's ionosphere. The event was recorded by satellites orbiting Earth. The flare from SGR 180620 outshone any other event recorded from beyond the solar system in a fraction of a second. It was a burst of gamma rays and X-rays so intense, it distorted the very fabric of our atmosphere. Astronomers first noticed the flare as a spike in radiation data. The signal was so strong, it triggered automated alerts across the globe. The source was identified as a neutron star with a magnetic field stronger than anything previously known. The Magnetar, SGR 180620, is located in the constellation Sagittarius. Its magnetic field is estimated to be around 1015 gauss, hundreds of trillions of times Earth's. The energy released was enough to power all human civilization for thousands of years. The flare was not a supernova, but a starquake on the magnetar's surface. The magnetic field, so intense it could erase a credit card from across an ocean, was disturbed, releasing a burst of radiation. This was not the first time a magnetar had flared. Similar events were recorded in 1979 and 1998, but 2004's flare was the most powerful yet, and it raised new questions about the nature of these cosmic monsters. The event confirmed that magnetars are not just extreme neutron stars, but cosmic powerhouses with magnetic fields capable of reshaping space-time. The flare was a warning. These stars are not to be taken lightly. The 2004 flare from SGR 180620 didn't just register on instruments. It punched through the cosmic veil. Satellites designed to watch the sun detected it as a gamma-ray flash brighter than the full moon. Earth's ionosphere, that thin layer of charged gas surrounding our planet, visibly rippled like a flag in a sudden wind. The energy released in 1/10 of a second surpassed the sun's total output over 10,000 years. This wasn't a distant event. It was a measurable, physical impact from 50,000 light-years away, a cosmic punch felt across interstellar space. Magnetars wield magnetic fields of 1014 to 1015 gauss, hundreds of trillions of times stronger than Earth's. Picture the magnetic field of a fridge magnet. It's strong enough to lift a paperclip. Now imagine a field a billion times stronger, concentrated on a sphere just 20 kilometers across. At a distance of 1,000 kilometers, this field would distort the electron clouds within every atom of your body, unraveling the very chemistry of life. The interior density is crushing. A single spoonful would weigh more than a mountain. Their surfaces are landscapes of frozen plasma under unimaginable pressure. Starquakes provide the clearest explanation for the flares. The magnetar's crust, a solid shell of iron and neutron-degenerate matter, fractures violently under the magnetic stress. Think of ice cracking on a frozen lake under immense pressure. This sudden shift disrupts the colossal magnetic field enveloping the star, triggering a cascade of energy. The 1979, 1998, and 2004 flares all align with this mechanism. The decay of that magnetic field powers the X-rays and gamma rays we observe, as the magnetar gradually cools over its short, active life of roughly 10,000 years. The link to fast radio bursts, FRBs, adds another layer of evidence. In 2020, the ASKAP telescope detected an FRB coinciding with a magnetar's burst activity. Astronomers now suggest that the violent magnetic reconnection following a starquake could generate these intense, millisecond radio pulses. Yet the connection remains suggestive, not definitive. While a magnetar source is strongly supported for some FRBs, the universe offers other potential culprits. The evidence points to magnetars as a key player in the FRB mystery, but the case is still open. Their magnetic fields still pulse, and the question lingers: what other secrets do these cosmic powerhouses hold? Starquakes explain flares, but the 2004 SGR 180620 event leaves a gap. That magnetar, 50,000 light-years away, unleashed a burst so powerful it briefly outshone the entire galaxy. Its energy, released in a tenth of a second, equaled what our sun emits over 10,000 years. Yet the predicted stress on the crust, fractured like a glacier under pressure, doesn't fully match the observed peak intensity. Lab experiments on neutron-degenerate matter max out at fields 1,000 times weaker. The magnetic field's decay rate also subtly mismatches the star's cooling timeline over its brief active lifetime. The evidence fits, but not perfectly, like a fingerprint slightly smudged at the edges. The FRB link rests on a single, tantalizing observation. In 2020, ASKAP detected a repeating fast radio burst simultaneously with a magnetar's X-ray burst from SGR 1935 plus 2154. This was the first direct correlation, yet no other magnetar has shown this dual behavior. Over 1,000 other FRBs originate from distant galaxies, lacking any known magnetar activity. While magnetars could theoretically generate these millisecond radio pulses via magnetic reconnection during a starquake, the universe offers plausible alternatives: colliding neutron stars or even exotic black hole phenomena. The correlation is strong, but the case lacks a definitive witness. Settling this requires capturing the magnetic chaos in real time. We need to observe the exact sequence: a starquake fracturing the crust, the magnetic field lines snapping violently, and the radio pulse generating milliseconds later. Current telescopes see only the aftermath, not the event itself. The square-kilometer array, when operational, might resolve magnetic field dynamics within the magnetar's atmosphere. Without that direct observation, we're left with circumstantial evidence, like a detective piecing together a crime from scattered fragments. Earth's ionosphere reacted to the 2004 flare. A magnetar's field could erase your molecular structure from across an ocean. We see the damage, but the mechanism remains fragmented. The magnetar hypothesis is the most compelling lead, supported by flares, FRBs, and decay rates, but not the final verdict. The case file sits open, evidence accumulating like dust on a cold case. What would dissolve your atoms first, the magnetic field or the question?